Hello guys, Mr. G here, and we are going to continue with the videos on these 50 marks of challenge question of momentum. It is important for the grade 12, so we're going to do it, and then next time we'll be doing another grade video, but we're going to finish with this one now. This is the second part of those questions. We're going to question 3, and question 3 said a 4 kilogram wooden object with a right angle triangle shape is at rest on a horizontal frictionless surface. A ball of mass 0.1 kilogram thrown horizontally at 10 meters per second collide elastically with the wooden object. As the result of the collision, the ball bounces vertically upward in no friction. Remember, also here the collision is elastic, and this is a good practice of elastic collision we didn't do before. Here is the shape, here is the picture of what happened. You have a ball that is moving horizontally in that direction as it's shown there, and it's moving at 10 meters per second. So the velocity here is equal to 10 meters per second. And then it's going to collide with that object, the shape. Then obvious, this object is moving there, as you can see it in the picture. It's moving in that direction, and then the ball is moving straight upward. Okay, but that you can see it there. Now we're going here say explain when a collision is said to be elastic. That is a very simple question, but we're going to answer real fast here. And then we said that a collision is elastic when both linear momentum and kinetic energy are conserved. So both of them are conserved. That is important here. Now the second question says calculate the speed of the ball immediately after the collision. So if we go here to 3.2, all they want is to calculate the speed of the ball after the collision, final speed of the ball. Now I want you to note something, but this is in the picture. The ball is moving upward, straight upward after the collision. So this final velocity here is what they're looking for. Okay, so now for this one, because it's a collision elastic, it's an elastic collision, the first thing we're going to apply is momentum. But be careful here. Momentum is only conserved in one direction. It cannot be conserved in both directions. Unlike kinetic energy, momentum is a vector and it will conserve in only one direction. But kinetic energy can be used because it is going to be conserved in both directions. So we are going to be starting here using kinetic energy. Why kinetic energy? Because kinetic energy is conserved in both, first of all, and because it is a scalar quantity, so it will give us the final velocity or speed of this object here. And remember, the conservation of kinetic energy say that the total kinetic energy initial must be equal to the total kinetic energy final. Okay, so what object we have here? We have that this is half mass final initial velocity of the object square plus half mass initial speed or velocity, let's say speed of the ball square is equal to, and then the same thing but final. Okay, so this is what we have, and then we are going to substitute the values we have here, guys.
Miss you, baby. So I stand up and speak just my mind. Oh.
And now here we have two unknowns. We don't have the final velocity of the object and we don't have the final velocity of the ball, but the final velocity of the ball in actual fact is a question mark here. So we're going to stop here and we are going to write like this one is equation 1. I am going to take away this 0. You know, it does not really make sense to have it there. I just wanted you to see it and you already saw it there. So we're going to stop here. And we're going to have, or call this one equation 1. It's quite simple, guys. Equation 1. So now we're going to go to momentum to calculate the velocity of the object, so we can calculate the velocity of the ball. So, law of conservation of momentum.
You whip up my appetite. Don't leave me here high and dry. Oh.
Now is the tricky part. I want you to notice that the velocity of the ball final have two directions. Velocity of the final have two directions, which is horizontal, and in this case the horizontal velocity of this ball is 0 because it's not moving horizontally, right? And the velocity vertically, which is upward. But that one is the one we are looking for. So the horizontal velocity of the ball is going to be equal to 0 because the ball is not moving horizontally. That is why we said we're going to start with kinetic energy, because momentum is a vector, velocity is also a vector. So here will be 0,1 multiplied by 0 because this ball is not moving horizontally. And this momentum is being used in the x-axis. So that is the only tricky part here. The rest is just calculation. That is the velocity of the object after the collision, and this one is what we are going to substitute in this equation 1. So if we do that, we have okay, and this is the final velocity of the ball, vertical upward. I hope you understand. It's not that bad. It's more intimidating than actually the real difficulty. Question 3.3. Calculate the average force exerted by the ball on the wooden object if the collision time is 0,02 seconds. And this one is not so bad. From 3.3. Now we're going to use for this one Newton's second law in terms of momentum. So we have that F net is equal to change in momentum divided by change in time. Change in momentum of the wooden block. So F net is equal to mass that multiply the final velocity of the wooden block minus the initial velocity of the wooden block divided by change in time. And then we have all the data. The rest is just substituting. Answer is 50 Newton, and that is the end of question 3. Okay, it's not too bad. It's not too bad. So question 3 is done. Let's go to the next question and final question of this video. Now, question 4 said the sketch below shows a missile launcher of mass 4,800 kilograms at rest on a frictionless horizontal surface next to the base of the smooth inclined plane. It fired horizontally a rocket of mass 1,000 kilograms and recoiled up the inclined plane, rising to the height of 6 meters. Okay, why the system formed by the missile launcher and the rocket is said to be isolated? That one is quite easy, so let's answer that one first. And the answer is because the net force is 0. An isolated system is when the net force is equal to 0, and that is quite simple. They say calculate the speed of the missile launcher after firing the rocket. And then for this one, let's have a quick look here. Here the system is isolated, so mechanical energy can actually be used, okay, for the launcher. And we are going to do that. We're going to use the mechanical energy, the conservation of mechanical energy, because the system is isolated. So we're going to come here and we're going to use the conservation of mechanical energy. So that one say that the total mechanical energy initial is equal to the total mechanical energy final. They don't specify how to solve it, so it can be used like this. So now here we have that kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. and we substitute this one. Note the following. This is what we're looking for: the initial velocity, the velocity of the launcher just immediately after firing the rocket. So we are going to substitute what we have here. And the answer is going to be 10,84. Now there is other options to do these questions. You can use Newton's law actually to calculate this work, doing Newton's law and equation of motion, but I think this is quite simple. I saw it in one of the learners, so I think it's the best way, it's the faster and it's the safer to do that. And then to calculate the other one, which is calculate the initial velocity of the rocket, we are going to use the conservation of momentum. And I'm going to fast forward because we've done it before. And this is the final answer of the question to the right, because they're asking the velocity. And guys, this is the end of this challenge question, that they were not so challenged anymore. So I hope it helped, I hope you understand, and thank you for watching. Thumb up, write comments, suggest. I'll see you next time. Mr. G here.